Hello, good evening. So we are back with our June meetup. Today, myself and Craig will be your host. I will be looking after. So I will be introducing our speaker, and Craig will be looking after all the questions and helping us. So we answer the question to the speakers, and we go from there. Thanks again for joining us. I know we didn't run this session like our usual second Tuesday, but we are in interesting times. But the good thing is, we managed to find a speaker, and it is an entertaining, informative, and really fun speaker to have. He's one of those guys that we don't hesitate to invite, and we invite him to speak here. Before I start, first of all, I want to thank all of our organizing team that we have in Sydney. They're really doing an amazing job to run the events, not only our usual presentation nights, but also the extra session for Ninja Nights that we do. The other thing, I would like to thank all our sponsors that we have, PwC, Google, Atlassian, and Amazon Information Security and SEC team. They have been amazing to support us for the past few years, and it's just lovely to have them. For those of you who have recently joined us, and if you're wondering what SecTalks is, it's a not-for-profit community, and it has been running for just over 7 years now. We have nearly around 8,000 members globally. We run technical talks and CTFs in different cities, and it's all run by amazing volunteers that we have. And of course, with the support of our sponsors, that they allow us to run these events free of charge for everyone to join. If just a bit of logistical stuff before we get to the talk today, we will be using, if you're part of our Slack channel, you can post your questions inside the Sydney channel. So there will be SecTalks_SYD. You can post your question there, or even better, you can post your question in our IRC channel. And if you didn't know before, yes, we do have a channel on Freenode where you can post your questions. If you have an IRC client, now you can head to that freenode.com, and the channel is #SecTalks, not single hash, it's the #SecTalks. If you do not have an IRC client, if you head to the sectalks.org website, there is a link to a web IRC client that you can use, and you can find all this information within the description of this YouTube video that you are watching at the moment. Now, today, before we go through the main talk and I introduce our speaker, we have a guest from Atlassian, Saoirse. She will be talking about some of the interesting positions that they have in Atlassian. And and then from there, I will be back and introduce our speaker. So, Saoirse, would you like to tell us a little bit about those roles?
Of course. Hi, everyone. Thanks, SecTalks, for having me. My name is Saoirse, and I am a recruiter at Atlassian, and I'm super excited to share a little bit of information about Atlassian security teams, and then our up and coming roles. In particular, one position. But I thought it might be helpful to share an overview of Atlassian's essentially teams, so that, perhaps if a particular team sounds of interest to you, you can reach out and connect with us and keep an eye on our careers page. We have a bunch of new roles opening in the coming weeks and months heading into the FY21 calendar year. So to dive right in, the security team's aim is to essentially protect and defend Atlassian's infrastructure, our products, and the networks from foreseen and unforeseen cybersecurity threats. The Atlassian security team is made up of 7 core teams across 7 Atlassian offices. So Austin, San Francisco, Mountain View, Amazon, New York, Bangalore, and of course, Sydney. I'll start with our ecosystem security team. So this is an application security team that works with our product development teams and Atlassian's marketplace applications and apps. So that extends Atlassian's products like Jira and Confluence through third-party integrations with apps. We also have our security intelligence team. So this is a defensive security team that focuses on obtaining, analyzing, and actioning security data. So that's to protect both Atlassian and our customers, of course. So things that they're doing on a regular basis, actioning incident responses, detection, threat hunting, and red team functions. Our corporate security teams, they're again another defensive security team, and they focus on hardening and defending Atlassian's corporate infrastructure. So a lot of the work that they're doing is, developing security corporate features, leading code reviews, managing the configuration and integration process of the various internal tools into our infrastructure. We also have a security development team. So this is both a backend and SRE team. So they build out the tools, the systems, the platforms that the broader security team are using. And on the SRE side, they're ensuring the reliability of those products and tools and everything that's created by the backend development team. Our compliance security team at Atlassian, or better known as the Atlassian Trust team, is an information security, compliance, and risk team. And they develop policies, procedures, and frameworks that ensures Atlassian upholds and maintains essentially best practice information security and privacy standards. We have a chief of staff organization that focuses on strategic programs for the security team. So that includes essentially security awareness programs and other organizational growth initiatives. And finally, to conclude with our product security team, and this is an application and infrastructure security team that works with Atlassian's product development teams like Jira, again, Trello, Bitbucket. We have 16 plus products within our portfolio today. So working with a lot of different product teams and implementing security measures that will enhance those product security and the kind of the posture. So we are looking to hire a senior security engineer for this team who has experience developing security architecture, threat modeling, and reviewing source code, remediating vulnerabilities, etc. So I just wanted to, highlight in particular this particular opening today and talk about that kind of senior product security engineer within our product security team. So to, just highlight the responsibilities that we're looking for, this application security engineer will kind of focus on writing automation, reviewing platform and service designs, finding ways to work with and enable engineering teams to think about a proactive approach and build secure products by default. So most of the code is written in Java, Python, or Go, and we are looking for someone who has extensive experience working in security specifically, has a deep understanding of application security, especially web applications, an ability to lead projects, large-scale projects, end-to-end, from start to finish. And finally, communication is key here. We're looking for engineers who have a strong ability to communicate ideas clearly and effectively, and to pollinate that information within the team and in the broader Atlassian organization and help up-and-coming security team members within the organization. So if you are aligned with any of those areas, interested to connect, I think my email address should be shared, but I'll pop it into the chat as well. You can connect with me via the Slack group. And finally, there's always going to be more information on the careers page, so don't hesitate to check that out as well. Thank you.
Well, thank you very much. I should say you guys do have lots of security teams within Atlassian. We will be having Saoirse throughout this session, so please do reach out to her. You can also find her on a Slack. If not, her email address is also, was overlaid a while ago. Thanks, Saoirse. So let me just quickly talk about a few other things in terms of things that you can find in SecTalks. If you are looking to present, the link that you can see there, j.mp/sectalks.cfp, is a place that you can let us know what talk you have. We do look for people who can also help us to create CTFs. There's a link for that. Please do help us with that. And yeah, a few other things. You can see all those links there. One thing I want to ask is, please be active on IRC or Slack throughout the talk. It really helps us to see how these talks is being received. We don't normally run our usual in-person meetups these days. So your interaction in IRC channel or the Slack would help us to know how the talk was received. If you have any questions, so please go more verbose there. Now back to our presentation tonight. So the speaker we have, I should say he doesn't really necessarily need any introduction. I'm sure most of you already know him. And he will be talking about side channel attack, specifically things to do with power consumption. So he will be looking at the theory behind the side channel attacks, and later on how things like power consumption can give a clue to an enthusiast or a security researcher how to find his way around. Now, one of the things interesting always about our speaker's talk is he's full of demos. So he talks about the stuff that he actually does, not just theoretical things. I don't know, Norm, if I just need to read your bio that you have sent to us.
If you like.
I don't really know why we keep inviting him, but he seems to be stuck at computers and definitely isn't good at electronics. So please do not listen to whatever he says. With that, let's just welcome Norm. The stage is yours. Please go ahead.
Yeah, thank you, Pedram, for the introduction, and thank you everyone for making the time to come to this talk. So I'm just gonna, there we go. So I'm going to be talking today about side channel attacks, specifically passive side channel attacks on power consumption. It's going to split into two parts. So I'm going to first talk about a high-level overview of how this works, some of the different general approaches that we can take to perform side channel attacks. And then I'm going to, in part two, we're going to look at some signal processing techniques to help you do these in practice. And I want to talk about how you can successfully use this to clone rolling key remotes without using RollJam. As a disclaimer, first of all, I'm not an expert at this. I'm just some dude with an oscilloscope. And so please be careful when you're playing with electronics, because if you're not careful, it's really easy to hurt yourself or damage your equipment. So please take care. Pedram mentioned demos, and I thought it's kind of difficult to demonstrate a power side channel using a live demo. So what I've done is I'm going to give you access to the software that I'm using, plus all of the sample data, including power traces from a keylock chip, which you can use to verify that an attack works. So I know what the key is. You can use this to check that if you want to do this yourself, you can check that the code is functioning correctly. What you want to do is git clone the code and then go to, so I think GitHub changed in the last 2 days. if you go to the tags section, you'll find there's some sample data. So if you click on 0.91 release, just download the zip files. Cool. So in terms of general principles, just to kind of start off, the thinking behind side channel is that the power consumption of a target depends on its internal state, like what it's doing. So for example, if you have a target chip and it's reading from its internal EEPROM, that's going to take a different amount of power and a noticeably different amount of power to when it's doing nothing. And this can get really fine-grained. So like when you do a move instruction, when you read data out of like program memory, if you are moving like a 0, it'll consume a different amount of power to if you're moving 0xFF. So this is kind of a core concept that we will rely on. So in these attacks, so we manipulate the target chip, or we we drive it, right? So we might like switch it on and off and read the output, or we may feed it plain text if it's doing like a crypto operation. So we have some idea of the internal state of the chip. And given our knowledge of the internal state, and given that we can measure power consumption, so we can perform a side channel attack. So there's statistical methods, which I'll talk through today, to show you how we can recover the key. So that's kind of a bird's eye view of the field. So how do you measure power consumption? So I might just show you this. I'm gonna stop sharing my screen for a second. So, okay, so you can use one of these things is what I'm using. So this is from the same guys who make Chip Whisperer, which is a tool for side channel and fault injection attacks. What this is, it's a target board, and it provides clean power to your target, and it allows you, like, instead of reconfiguring your target every time, you can. It's very useful. Like, you can set jumpers, for example, to select the clock source that's being fed into your target. So like instead of having to make new target boards, you can just flick some settings on this and change how your target behaves. All right. So back to the slides. Yeah. So I can present. So the way this works, so what I've got shown here on the right, I think there's a laser pointer function. So what I've got shown here on the right is a key lock IC. This is the key lock IC that I targeted. And I'm using the target board that I just showed you to provide clean power in, and I use a shunt resistor. So what the resistor does is that you insert it in the ground line in this particular case. And so what'll happen is the current passing through the chip, depending on its operation, will change. And because of Ohm's law, that'll convert into a voltage drop across a resistor. So you can, with an oscilloscope, you can measure one end of the resistor, and the other end just hooked to actual ground. And what you get is the changing voltage will reflect the changing current consumption of the chip that's changing because of the key that it's using. You can also do a VCC shunt as well. So this is not the only possible configuration. Another way to convert the current consumption into a voltage drop is to, like, if you don't use the resistor here, you put a resistor on the VCC line. That will also work, particularly if there's nothing else drawing power from the same power line. So that's something that you want to isolate your target. So if you put the resistor here, you can also measure using something called a differential probe to measure the voltage drop across the resistor. Or you can set your oscilloscope to AC coupling, and you can just measure the voltage at the end that's closest to the target. And that will get you a power trace that corresponds to the power consumption over time. So the output of that process is what you'll see if you go to my GitHub and you download the sample traces. So that I've already done that for a couple of targets, doing AES and doing like key lock output. So one way of measuring the current consumption is via like a shunt resistor. The other way is electromagnetic leakage. So what happens is that there's also a corresponding and proportional change in the electromagnetic field around the target chip. So you can use this. So this is an H-field probe, again from the same company, UAE. You actually don't need one of these probes, right? So it's really easy to make an EM probe. And let me just show you if I can exit PowerPoint properly. Hold on, give me a sec. Okay, so this is also a valid H-field probe. It's a paddle pop stick plus some wire that I just made into a loop, into a couple of loops, and just put some sticky tape around it. That works. So having a pre-made probe, so there's a couple of manufacturers that make pre-made probes. They're really good if you want to reproduce your experiment, because with this, if you drop it, the shape of the loop might deform. Or if you wind a new coil, the shape of it might be not exactly the same as your last one. If you want to repeat your experiment over a long period of time, it may be worth just investing $30 to go get an actual pre-made probe. Okay, that's a PowerPoint. Okay, cool. Slides are up. Okay, so let's dive into how this can be used. The simplest case is there's a technique called simple power analysis, which is basically where you look at the power trace and you eyeball the password. So because different operations take different amounts of power, you can just look at where it's taking lots of power and you know that it's doing operation A. Or you take a look at when it's taking less power and you know it's doing operation B. For example, so I made a target, which was a an Atmel ABR chip doing string compare towards a fixed string of, I think it was password 01. This is what happens when I enter the string lol. So if you have a look at this, and then if I enter pass lol, so 4 of the characters are correct, you can immediately see that the string compare operation is taking longer. And if I enter even more characters of the correct password, you can see that there's a much longer period of operation for the string compare. So in its simplest form, power analysis might seem like a really intimidating field, with a lot of maths behind it, especially if you read some of the academic papers. But conceptually, it's really easy. This works. Cool. So I wanted to go into AES. So AES is typically used as an example. So it's nice and easy. You can kind of compare code with other implementations because everyone uses AES as an example. We're going to first have a look at the initial steps of what happens when you do AES. So for reference, I'm looking at the 128-bit version. You can use a larger key size. It kind of doesn't make a difference because all it means is that you just repeat this process some more. So what happens is you get data coming in to the AES encrypt core function. So this is from AVR CryptoLib, which is a cryptography library for low-powered computers, for low-powered ICs. And so what happens is that your plain text gets XORed with a key. So that's step 1. And it goes into the bulk of AES, which is the AES comes into 10, it has 10 rounds. And so for each round, what it does is that it will take the plaintext XOR the key and then use that as the index to a lookup table. So that's over here. So the key, we don't know. We know the plaintext because we, as an encryption oracle, we can feed it. We can feed plaintext into this algorithm. We don't know the key, which is fine. We'll work that out. And the S box is public knowledge. So you can go to Wikipedia and download the S box. So you can look at an AES implementation and download the S box. And that's fixed for all normal implementations of AES 128. So just as a side note, so a 32-bit version of AES, there's sometimes an optimization known as T-tables, where they join several steps of the AES operation into a giant lookup table. We won't be talking about that, but the same principle applies. And in the code I shared earlier, there's like the attack against T-tables is already made. So to recap a bit, we've got now, assuming we know the plain text in and we want to find out the key, we know the S box. We're going to call the output of that S box our intermediate value, and this is what we're going to attack. So what we measure, because we can measure the power consumption while it's doing this AES operation. We don't know what the key is, that's fine. And so we don't know the S box output. We don't know the intermediate value. We do know the plain text, but we do know, we can take a guess at the S box value, right? So we know the approximate Hamming weight. So what happens is that the power, the leakage part of AES in a typical implementation comes from when it's moving the result of the S box operation out of program memory into wherever it needs to move it to. And you can know the Hamming weight, or you can approximate the Hamming weight via measuring power consumption. And so what the Hamming weight is how many ones are in that output. So you don't know the output, but you have some clue of what it is. What we can do, because we don't know the key, right? And so, sorry, just before I go on, so we only attack one byte at once. So the key, like, instead of attacking the entirety of AES 128-bit, we just attack like effectively AES 8, and we look at the first byte of the key only. Because there's only 255 possibilities for the 256 possibilities for the key, we brute force locally. We go, hey, if the key is 1, calculate the S box output of what it would be. Like, because we know the plain text and because we guess the key, we can guess the S box output and then calculate the Hamming weight. Like, we just count the number of ones in binary. And we do that for every key from 0 to 0xFF. And then, so what happens is that because the Hamming weight is like proportional to the power consumption, we just look at like for which of the keys does our estimated power consumption match what we actually measured. And there will only be one where it correlates strongly. That's the basic principle of correlation analysis, or CPA, so correlation power analysis. And in order to recover the entire key, you just do that like times the number of bytes that are in the key, depending on if it's AES 128, 256, whatever. I can show you this now, in fact. So I've got some demos prepared. Okay, and okay. So what you'll see is I've got a sample key. So this is the key that I put into the firmware. So like I know when my attack is coming out correctly. I took some. You
mind to zoom in a bit?
Hey, sorry, what's up?
Just zoom in a bit if you don't mind.
Zoom in. Sure, we'll do. Could it be better? Hopefully everyone can see that. So I have the key here. You can grab that out of GitHub. This is what I'm going to show you first is what the power consumption looks like for the AES operation. The rest is specified in the tutorial. Then the dash C. The dash C is, I can't remember why I called the dash C, but it selects which trace. I've got 200 traces in here, I think. And it selects which traces you want to see. So we only need to see one. And what you'll see is something like this. Oh, TK doesn't want to scale. All right. Okay. You can actually see, like in power consumption, like you can look at the rounds of AES already. We only need to target the first round, but I've included all of them as reference. And so what we can do, we can perform the correlation attack against the first round of AES. So we know that it's going to be, like, for example, the first round, the SBox operation should be about here from memory. And I'll talk about how to, like, ways to find out where that operation is in a bit. Okay, so we close that. Okay. And now we use CPA.py, which is a wrapper for correlation attacks, and you can load different like Hamming weight prediction models into this. So we go F again. We go -A to load an attack model. We need an offset, which specifies, so what happens that you can perform the attack against the entirety of the power trace, but that takes a long time. It is not necessary in this case. We only need a few traces, and I think it worked when I did it earlier with 8,000 points. Somewhere here, yeah, 8,000, okay. So if we hit enter, what it'll do is that it will load everything into memory, and it will start extracting the key based on the process which I showed in the slides, but not automated. You can see that the key, not that part, but the key is the actual key. There's 16 there. Keep going, 28. And so if you're using this software, or any toolkit which does correlation analysis will typically give you not just a guess of the key, it'll give you these numbers over here. What these numbers, the floating point numbers, mean is this is the Pearson correlation coefficient of basically it's a number from -1 to 1, which indicates how closely the expected power consumption for a given guess at the key correlates to the actual measured power consumption. A value of 1.0 means that you're exactly spot on. A value of 0 means there's no correlation, so the two are unrelated, like your guess does not correspond to the actual power consumption. And a value of -1 means there is a negative correlation, which is also good. A negative correlation means that if in your model you've said, like, the more Hamming weight something has, so each one consumes more power. If that's the opposite, and in fact each one consumes less power, you get a negative correlation coefficient. What I've done in my toolkit, I've just taken the absolute value because it, like, both extremes are good. The further away from 0, the better. So ignore that for a sec. What you'll notice for each of the key bytes that have been selected, there's typically a noticeable jump between the first, the correlation coefficient of the first key guess, that's the thing that the tool thinks is the right key, and the second and third key guesses, which it's placed there for context. So sometimes what you get, due to various reasons, is that two guesses at the key will produce similar correlation results. In that case, you can look at these numbers here, the correlation coefficient, and where you've got two that are relatively close together, you can go, okay, there's a high likelihood that's incorrect. That's okay, quite frankly, because, like, given the amount of key bytes that have been correctly selected, like, you know, you can brute force 2 characters. So what this is, so what you'll do if you're using my toolset, you'll get this graph as well. They basically show, like, this is the peak of correlation. So for each key guess is plotted along the x-axis, and the correlation value for that key guess for the hypothesis versus the actual power consumption is plotted in the y-axis. Big spikes mean that it's good. And you can notice sometimes you can notice potential false positives by 2 spikes being very close together, or missing spikes for entire key bytes. So this is just a visual indicator to help you estimate the amount of error or the amount of correctness for a given selection of key. Cool, and I'll print out the key here. I think this one is all correct. Looks pretty right, which is good. Sometimes you'll notice that, like, and I'll show you an attack later on where it's not correct, but you can identify the bytes that are wrong. Cool. So back to the slides. So that's correlation analysis. The commands that I've shown here in the blue, over here down the bottom. So atmega-em7.traces is captured with an electromagnetic probe, just on like an atmega 328, so one of those like standard Arduino microcontrollers that you get from JITTER. And so you'll like all the information that you need is within the first 8,000 data points of each trace. So that's what the -N8000 is. And I've also done this, which is using a shunt resistor. I think this is a 50 ohm resistor across the power line of the same processor. And you'll see that there's, like, it kind of doesn't matter what method you use, that's the end result is the same. And the reason why this is so important, especially for cryptography and like secret keys and whatnot, is that you've suddenly, through this attack, you've reduced the brute force space from 2 to the power of 128 to 16 times 2 to the power of 8, like, you know, which you can do at home. Cool. So moving on. So here's like the results that you get, which I just talked about. There's also differential analysis, which is another way that you can view the same data. In this technique, what you do is that you take your plain texts, and then for each key, you guess what the intermediate value, what the SBox output is, and then you run it through something called the distinguisher function. What the distinguisher function does is that it groups things into two groups, into like yes or no. And the distinguish function is a way of breaking down the power consumption. Like it goes, does this power trace meet a specific criteria? Does the Hamming weight of the intermediate value exceed or equal 4, for example? This could be anything. There's a lot of varied distinguisher functions that you can use. You can use like the parity of a bit, for example. You can use like is the intermediate value even or odd? That's another valid distinguisher function, and this will vary depending on the target that you're going to attack. What you do with that, and please excuse the handmade diagrams, you split all your power traces. So remember how we captured a whole bunch of power traces before, and we split them into groups depending on the distinguisher function for each key guess. If you have a good distinguisher function and your key guess is correct, what will happen is that there'll be points where you'll have correctly sorted them into two groups, and one group will have like peaks in power consumption which are not present in the other group or are different in the other group. And when you average all of the traces together in each group and then subtract them, you'll see a spike. There'll be a point at which, because you've distinguished the two groups correctly using your distinguisher function, you'll be able to look at, you'll immediately spot, you go, hey, there's actually a difference between the means of these two groups, and wherever that difference is strongest is the correct key. For the same distinguisher function, if the key is incorrect, the intermediate value guesses will also be incorrect, and it will be effectively as if you have sorted the groups at random. When you sort the groups at random, there are no significant, or there are less significant peaks in the difference of means. So if you've sorted them correctly, it'll look like this bottom diagram, and you'll notice that there are big differences. If not, the two traces will just be jumbled together, and you won't see anything. So I've got another test trace. So this one's a bit larger. I can't remember why I captured so much data at the time. This is against another microcontroller using the same key. And I'll just show you how this attack works against that as well. So escape. Here we go. Okay, so I'm gonna copy the command, Control C. I find this a little bit faster time-wise, but given the size of the trace, this one's actually a little bit slow. You'll see that it's recovered the first byte of the key correctly. It is in fact 2B, and I think the second byte is correct as well. Whenever it decides to do its thing. No, it's not. The second byte is not correct. But you can see, you can start seeing, like in the first byte, what this value is the maximum difference of means. So that means out of all the key guesses, that floating point value is where this distance is the largest. That's what we use to confirm whether we've correctly recovered a key byte. And as you can see here, there's a little bit of jump here. Here's not so accurate. Like with this one, you're like, okay, maybe the key is 15, maybe the key is 96. You don't know. But you can be pretty sure like the key is not 21. So sometimes like you will get like incorrect guesses. And that's due to a variety of reasons. It could be due to poor capturing, misalignment of traces, which I'll talk about a bit later, like electrical noise due to like various causes of electrical noise. And so sometimes it will be incorrect, but I think brute forcing 2 characters for each byte of the key is a lot better than brute forcing all of the characters for each byte of the key. Yeah, so you'll start noticing there's some error here, which is fine. Like that's how this goes sometimes. Okay. And yeah, so you can like all the data is provided for you if you'd like to do this, and you can play around with the values, see what like different results you can get. Sometimes what will happen is that if you make this range too broad, what will happen is that because you've included too many data points, there's like unrelated data points, unrelated operations that are taking place, which introduce false positives because they act as sources of electrical noise. In this sorting scheme, like I kind of don't care what happens here. I only care what happens in the peak. So sometimes one of the solutions is narrowing down the range until you can find like, here's the instructions that are leaking information. I just want to capture this. Yeah, and here's what I did earlier. I think I did it with slightly different parameters, but like you can see again, there's some error here. But again, like you can notice, you have some indication of how much error is in a given guess, which is one of the really good advantages of this method. You don't have to recover the entire key often, because sometimes if you're able to check your guess, then you can just locally brute force the rest of it, like 2 bytes of brute force, whatever. Okay, I'm gonna take a pause here and just ask, are there any questions particularly about correlation analysis? Because the next part depends on correlation analysis. And just this thing here is the same graph that we saw earlier, with each peak showing the difference of means, the maximum difference means for a key bit. And you can see in this that like there's kind of peaks, but they're not that strong. There's one peak for which there's an extremely, like I don't know specifically which one it is, but there could be other sources of noise which have meant that the other peaks are not as strong. I haven't investigated into exactly why. Cool, so are there any questions at this point?
I haven't received much questions so far, but I do like to ask in terms of, you talked about 2 different sets of correlation analysis, just a bit of 101, at least for me to understand, revisiting some of those differential analysis that you did.
Yep.
And the second thing was, you also assume that you know the plain text, and also you have some assumptions that the key length is between 0, 0 to FF. Was there any particular reason you have those set there?
Okay. So I've assumed that I know the plain text, I guess just for demonstration purposes. What I'll show in the next part is in attacking key lock, we won't know the plain text, we'll only know the ciphertext. So I've just said I know the plain text just to make this easier to discuss. With the key length, so the key length will vary depending on, like if you use AES 256, then you have a much bigger key. In this particular case, and when we're attacking AES, the key length doesn't matter, because all it means is that there's like additional key bytes which you have to do the recovery for, which is fine. You can just extend the loop. And the maximum value of each key byte being 0xFF is just, if I'm assuming that each part of the key is 8 bits in length, which it is in the case of AES 128, 8-bit, then like that's how much I have to guess. This algorithm, the technique is applicable to any size of key, any maximum value of key. Is that what you're asking? Does that answer your question?
Yep.
Excellent.
And that two differential, yeah, the one was around grouping, and you did the analysis between the mean value, and the other one was just individual values. Just wondering, yeah, which one do you find more effective in that term?
Okay. I find the results vary. There's not one thing which is more effective. I find correlation analysis is a little bit easier to do because it's a little more tolerant to noise. And I don't know, I prefer it. I like the algorithm better. It's just personal preference. Both are effective, and it's worth, like when you're attacking an unknown, like a black box implementation, I think it's actually worth trying both if you can. Sometimes one won't work. So in the keylock example, differential analysis didn't work for me. So yeah, both are valuable. Cool. All right, so I'm gonna continue on. Where were we? We were here. Okay, the next part, we need to talk a little bit about signal processing. And the reason why is, like, when you do power analysis, you're not always going to have perfect firmware that you control. And sometimes there's like random source of noise, and that's just like, that's life. Particularly if you can't control the implementation, there's other things happening inside the target that like you're not able to stop. So there's two forms of noise, generally speaking. There's sideways noise, so jitter. And what that is that when you capture power traces that won't always be aligned, you can see here that the peak of two of these, the clock cycles, are slightly misaligned. So any amount of this, even if it's just like 3 samples to the side, will severely impact the power analysis. Like the statistical concepts behind it will not work if the traces are misaligned, and they'll fail pretty horribly. You'll notice that the correlation goes like almost to 0. And this can also be caused by clock drift, which what happens is that internal to a microcontroller, they might have like an internal clock. So you don't feed it a clock signal. It just like tries to count time by itself, but it's not that accurate. It kind of doesn't matter, because inside the black box, as long as it's within its own tolerance, then like it doesn't matter what the clock is. It can be inaccurate as long as it works. But for power analysis, we have to counter that by pre-processing the signal to line up the power traces, especially on our points of interest. 2 ways we can do that is by, you can kind of take the traces and then slide them back and forth, almost like you're laying one on top of each other, like tracing paper, and you minimize the difference between the 2 traces. So that's called the sum of the absolute difference. It does what it says on the tin. You actually minimize the sum of the absolute difference. You can also maximize correlation. So what that means, I guess in greatly simplified terms, is that for the 2 traces, you want, when one trace goes up, the other trace goes up. One trace goes down, the other trace goes down. And when you line up the 2 traces, again, like tracing paper, you slide them back and forth. When you've got them to a point where they've got the maximum correlation score, you know that you have correct correlation. You can also fine tune it by lining up peaks. So you just take like a local maxima and you make sure they're at the same point. That's another tool that you can use. Depending on the type of noise, like there's not a single way to do this. It'll depend on your target. In the software that I've shared, there's a preprocessor.py module, which will help automate a lot of this process. Also contains some code to, sometimes what will happen is that because you're triggering, so the triggering is when you start capturing power, if your triggering is inaccurate or you're unable to get a stable trigger, you can only like, I'm triggering from when I send my plaintext or when I press a button plus 4.5 milliseconds, and you know that there's clock drift, you can slide it back and forth, and you know how long one clock cycle is. You can just slide it by multiples of the clock cycle. Sometimes that helps, particularly when attacking black box targets. So in the earlier case with AVR, because I control the firmware, I just go, hey, set this GPIO line high when you're about to start your AES. So you don't need to do any alignment on the Atmega traces, the sample traces. For the Keylock Tracer HCS 301 trace, I've already pre-aligned that for you. But like if you do further captures yourself, you'll notice that this becomes an issue. There's also vertical noise. So what this is that the actual amplitude of the peaks changes. This can be due to a variety of reasons. For example, like an internal voltage regulator or other internal components which you do not control. One way to reduce this noise is using a FFT to view the signal in the frequency domain. And what you'll see is there will be a peak where the clock frequency is, because at like each edge of the clock, there will be like an energy leak. Or no, there will be a change in energy, and you'll notice that this effectively becomes a given, like a frequency peak inside the signal. And you can use different methods to reduce noise. So what you can see here, so this is from one of the AVR traces, which you shouldn't need to denoise. You can see there's a little bit of low frequency noise. Okay, so what you can do is you can use a hardware bandpass filter. So you can buy them from places like mini circuits. And so it's really good to use a hardware filter in this case, because when you digitize a signal, you lose information because of like the process of converting an analog signal into ones and zeros. Preprocessor.py also offers some like software options for doing like a bandpass filter, low pass filters, and whatnot. One other way that you can use is if you can use a larger value shunt resistor, you can amplify the change in power consumption. So because of Ohm's law, V equals I times R. If the R is bigger, V will also be bigger, and I kind of remains static in this case. So that's something you don't control. By increasing V proportional to I, you can reduce the impact of some noise. Cool. So moving forward, using a low pass filter. So what a low pass filter does, so you would have seen this if you've played with like SDR stuff. A low pass filter takes a signal and then blocks all of the high frequency signal, all the high frequency components. What it means in practice is that it blocks little tiny changes in the signal and gives you like the big changes. What I've done here is I've taken one of the AVR traces and I've applied a low pass filter of I think 6 megahertz. So what you do here is that you specify a frequency and the sample rate, and it will block all high frequency components kind of above that cutoff frequency. And you can see immediately that because there's not so much like high frequency change, because we're not looking at like the minute details, you'll immediately see that the actual operations inside AES become clear. So AES comes in 4 major steps. So there's, I should probably know this by now, but there's the S-box, the sub-bytes, there's shift rows. So I'll have a laser pointer here. So there's that, I think is the sub-bytes operation. This should be shift rows, the second step of AES. This is mixed columns, the AES mixed columns operation, where it shuffles your states around. And then there'll be a little tiny blob here, which you almost can't see, which is basically you add in another round key. And you see over here, without that filtering, that's a little difficult to see. So a low pass filter can be a way to extract major features out of a power trace in order to help you like aim your correlation analysis. So you can go, I only care about the first 7,000 samples, or the point of interest does not begin until sample 10,005. It helps make these attacks quicker. And you can also just use this at a high level to just locate like features, like code paths that are being taken. If you notice in a power trace, if there's significantly different power consumption based on what you input, then like you can use a low pass filter to reduce the impact of like your constant background noise. You just go, okay, I know what the overview of the code trace looks like from a power consumption perspective. Okay. I can show you. It's probably worth showing you plot.py as well. So, okay. So plot.py is like a generic trace viewer which I've created. Okay, so I'm going to view the AVR power trace of it doing AES. I'm going to choose, I don't know, so like 3 traces. It doesn't matter, choose any. And if I just do that, you can see, and like it's not very detailed, but does TK want to play? No, okay. So you can see the rounds of AES here. And then here's where AES ends. I've captured the whole AES encryption for you. But if we can apply a low pass filter just directly from this tool. So low pass, and we're going to use a cutoff of arbitrarily 60 million. I think the actual clock frequency is 16 megahertz. Like for low pass, because all you want is like the big structural changes to the code, you can eyeball the number. Like you have a play around. So the sample rate of the file was 125 megasamples a second. So that's our sample frequency. And this is the order of the band of the low pass filter. So a first order low pass filter is fine for now. Okay, and you can immediately see that the blocks inside each round of AES become a little more clear. You can also use this tool to do this. So you can zoom in on a specific trace using O. So O for offset is where you want to start, and N for the number of samples. And you can zoom in and look at a trace in detail. You can go really fine detail and look at individual clock cycles if you like. So we'll remove this. We want to see the actual detail. And you can kind of see it. You can kind of see some of the clock cycles. It's probably not very clear. Maybe it's easier if I show you just with 1 trace instead of 3. Oh, no, that didn't help. But what you'll typically find is you'll see the repeating pattern of the power consumption across each clock cycle. There's some other tools. I can't remember all the arguments off the top of my head. -F will give you like a frequency domain view. So this is really easy for locating noise. I mean, you can see like harmonics of the clock frequency as well. I think anyway, have a play around. Plot.py has, like, it's one of those pieces of software which has grown over, I think, 2 years and a bit. So there's a lot of options for that. Okay. So I've got instructions for how you can do an experiment which simulates time-wise noise on one of the traces. I'm not going to go through it now because unfortunately it takes a while to run. And there's a fair bit of content to cover. But you've got the sample data. What will happen is that if you add a little bit of noise, a correlation attack and a differential attack will completely fail. And then you can recover it. So I've provided a sample recovery file. So the noise is random, so everyone will get different results. But you can try and do the thing where you line up the two traces on top of each other, and the preprocessor.py automates that all for you. And what you'll see then is that the key will be recovered again. It's a bit of a mistake here. For F, you need to supply the output of this step, but I will correct that and upload the slides. Okay, so let's kind of get into the bulk of what I wanted to talk about today, which is the implementation of this against keylock. Keylock is, it's not used in, like, it's not all over the place anymore, but this was used and still is used today in a lot of like garage doors and some car doors. This is what roll jam attacks. So it's a rolling code. And the idea is that you can't predict the rolling code. So what roll jam does is that it blocks the code once and captures it and then replays the code. What I want to show is there's a way to extract the secret key and just clone your own remotes permanently. This targets a chip called HCS301 by Microchip. There's actually, there's other implementations. If you go on like AliExpress and search for a keylock encoder, sometimes you get some like knockoff implementations for which this technique should work, but you may need to adjust it and adjust how you capture power from the device. Like it might do the operation at a different time. As a convenience, I've also provided some Arduino sketches which allow you to program a fixed key onto your own HCS301 chip. So I can show you the setup, and I'll stop sharing. So your typical rolling key remote looks like this, and so there's a little light when you press the button. Is it right? No, it's not. It's this side. Okay. This is the target chip. So what happens that when you press the button, this chip does its internal keylock algorithm, and over here is the RF clock. So this chip doesn't actually generate. So these typically operate like 433 megahertz. This doesn't generate a 433 megahertz output signal. It just turns the RF transmit on and off. So it's very slow, like kilobits a second speed, I think. And you can just you can read that out. There's an Arduino sketch in the provided source code for you to read that out as well. I'll show you this as well. So this is what you want to do, and forgive the terrible craftsmanship, is I've isolated the target. So there's the HCS301 chip. Over here, this green wire is a power source in, and there's a resistor on the ground line. This is a trigger. So what happens is that this trigger board, which is it's just an Arduino in a more convenient form factor. This will send a signal to this as if I'm pressing the button to this line here. And then over here, there's a little fine wire, which you probably can't see, this thing. So that wire will read out the output of keylock. Okay, so I'm going to share my screen again. Right. So yeah, if you want to play with it, or if you just want to program your own keylock remotes, you can use the tools in the targets HCS301 folder. So keylock is a little bit different from AES. Keylock operates using a 64-bit key and a 32-bit state. And for each round, so there's 528 rounds, and for each round, it'll calculate one new bit. One gotcha is that the key that you program in is not the actual key used in the encryption. The key is actually shifted slightly. You'll see the order of the bytes has changed a little bit, but that's okay. Like if we know the shift, we could just undo the shift and you can program your own remotes anyway. So I started this adventure by looking at what other people have done in the past. And strictly, so I wanted to look at what side channel attacks had been done against keylock. There's a paper, I think in 2008, where they described the first iteration of this, which basically is what's described here. So here's the capture setup. Here's the diagram if you want to build the same capture setup that I've got. So there's, and I'll show you later on, there's another GitHub repo, so Mark Invalid, GitHub/Mark Invalid, where he's implemented like a similar attack, which I'll go into in a bit. So when I initially captured power, so this is, I failed horrifically at this step. When I initially captured the power, I used, I think, a 10 ohm shunt resistor. It's always safer, in my opinion, to start with little tiny shunt resistors, which don't impact the supply of power that much. That you want the chip to maintain regular operation as a starting point. So I put in like a little tiny resistor. And because the resistor was so small, I was unable to see like the core cryptographic operations in detail. So if we go here, what you'll see is that there's a couple of blocks. So this first block is a wait time. And in the datasheet for the official documentation for HCS 301 goes, when you press the button, it waits for a fixed period of time, and then it tests, is the button still pressed? And this prevents accidental activations. And like it's rolling code, so you really, really want to prevent accidental operation, because if you accidentally do an iteration of keylock, the next iteration of keylock will be incorrect. So it's called, so this is typically called debouncing. And this part underlined by red is a wait time, where like it's not doing much at all. This part in the middle, underlined by green, is according to the 2008 paper, it's a operation where it's reading, it's writing to EEPROM. It's writing the counter to EEPROM. And the way that they figured that out, which I think was pretty smart, is that if you drop the power supply during this operation, the next time you press the button, the same rolling code, like the rolling code won't move forward, which indicates here's where it's storing like persistent information. It's if you deny that part of operation, it can't store the fact that it's generated another rolling code, it will generate the same one. So over here, actually, so I've underlined it, this part in yellow, and I thought that this was the keylock operation, which is incorrect. There's actually two parts here, which I'll show you in a bit, which I couldn't see because the shunt resistor was so small that the current consumption was just like, it wasn't amplified enough for me to be able to locate where the encryption actually ended. Over here in blue, you can see the start of the RF transmission. I understand this is for gain control, but for our purposes, we don't need to worry about that part. We can go, as soon as we entered into this part, like we know we've gone too far, because at that point, the key encryption is done. It's just sending out the key. So we don't need to worry about that part. I then used a much bigger shunt resistor, and forgive the poor screenshot. What you can see is that, so here's the EEPROM. See how there's a large change in power consumption? That's the EEPROM operation. That's actually this bit. Over here, though, is where it gets interesting. So see here, it's kind of like one block. Over here, you can distinctly notice that there's two blocks split about here. This is where the encryption operation occurs. This was identified in both the 2008 paper as well as the GitHub repo, the Mark Invalid's GitHub repo. But I think there's been an implementation change since then, because what I found was that this is like several milliseconds shorter than the previous attacks against keylock. At this point, I think I want to talk about the test vector leakage assessment. What this is a statistical test called Welch's t-test. And what that is that it goes between two groups, is there a statistically significant difference of means? When the value is above, when the absolute value is above 4.5, typically it'll mean, yes, there is a significant difference between the two. It means that you're able to, you can group things, right? So you can go, can I find out the last bit of the keylock output? And what you do is that you group, because you know the output, because you emulate pressing the button and you read the keylock encoder's output, you can sort them into two buckets of odd or even and apply this t-test to them. And it should come up with something like this. There'll be a point at which there'll be a really big spike, and you go, okay, I've located the point at which the chip is somehow processing, storing, or using the the final bit of the keylock output. So at that point, you can probably go, like, that's an indicator to go, here's the end of the encryption, because at this point it knows the entire ciphertext. You can also use this to locate where an encryption operation is happening, or to fine tune where an encryption operation is happening, because you can control the grouping. You can go, I want to group on the like a known key and the first SBox output for AES, for example, or the first intermediate value. And where the first t-test spike is, that'll be where there's significant potential energy leaks coming out of the microcontroller. So you can start attacking at that point. Please be wary that this is not infallible. There are false positives and false negatives. So this is a good indicator, but please don't 100% rely on it. The reason why this is important is because I wanted to use this to confirm the previous results of attacks against keylock. Because the first step was applying the t-test to the plain text output. So that when the actual rolling code that's transmitted, they wanted to do a t-test across that. And so this is a screenshot from this repo up here. And what it shows, so this is using the Chip Whisperer software, albeit an old version. I don't know whether you can port the code to new Chip Whisperer 5, maybe. What it is, this is a t-test across the plain text output. And you can see that for each bit of the plain text output, there's actually like really big spikes for the t-value. And so this means that at this time, the actual bits of the final output of the keylock operation are being manipulated somewhere in the chip. So it means that you can isolate your attack to this area, because this contains, or should contain, all the information you need to make an initial guess at the key, because it's using the key to calculate the entirety of the plain text. What I found was when I applied the same test, I was completely unable to get any meaningful results. You'll notice here that there's a little bit of a spike towards minus 4.5. And what I found was that like I could replicate the experiment by performing another set of power traces, and I wouldn't get a consistent spike here. So to me, I looked at that and I was like, okay, if it's not a reproducible spike, then it's probably just a false positive. So I set that aside. But what ended up working for me to actually extract the key was by grouping the guess. What that means, so in the original attacks against keylock, we attacked one bit of the key at once. So what had happened for each round is you take a few of the bits, so over here, a few of the bits from the original text of the internal state. So the internal state is like, it starts off as the plain text, which is like the data sheet will talk about how this is calculated. It's a fixed value of like the state of the buttons and a counter value. So this is known, but not exposed to the user. So it takes the plain text, it takes a few of the bits and passes them through a function which generates a 1-bit output. It takes a last bit and this bit here, and it generates a 1-bit output. And it takes 1 bit of the key and mixes them together and passes that to the last. it passes them into the shift, into a shift register. So the state gets shifted, and then one new bit gets added on to the end of that. So that's how key lock in general works. So what I've done, what you can actually do is you can group the guess. Instead of attacking a single bit at once, you can attack 8 bits at once, which will get you much higher accuracy. And it's because, if you recall what we were talking about earlier with correlation analysis, the correlation is against the difference in Hamming weight of an intermediate value. But if you attack it bit by bit, the difference in the Hamming weight is like 1, because there's only one new bit. And it's really easy for noise to like suppress that, and you're unable to see what the actual difference is. Over here, if there's 8 bits of difference, you can start like seeing the differences. So if you bear with me. Okay, so I'm going to first show you what the key lock looks like using plot.py. So this is the power trace at the end of the key lock encryption. So again, we use plot.py. So this is the power consumption towards the end of key lock. You can see the actual individual rounds of key lock being performed, or clock cycles. I think a couple of those are in a round. Towards the end, so the reason why there's like a weird orange spike here is because I've realigned the traces. And the way that my code does that is by sliding the traces backwards and forwards. And so this is what happened when I've had to slide one of the traces backwards a bit. So the data here comes, the data on the left, like the samples on the left at the start, kind of get shifted to the end. Okay. I can show you the TLVA. So it should be TVLA, but the T, like I misspelled it years ago, and it's there now. Traces at the key lock, I think. Okay, and what you'll see is that like there's not really significant spike. Like there's kind of a spike, but it's not significant enough where I can go, hey, yep, that's like a definite hit. Like there's a definite statistical difference in the difference of means between two groups, between even and odd, between the last bit of the output. You can also as part of this particular module, as part of key lock, you can also specify intermediate key values. So you can go key guess 0x11, for example, and it'll actually pre-calculate, I think, the first 8 bits of the key. Or not. Okay, never mind. Where was I? If we go back to here. So I'll show you a bit of the code. And this is how the guessing algorithm is implemented. So if we go support attacks lock.py, so I've got some test code. So I'm going to be using a correlation attack. And what it does is it generates an intermediate value. So this calculates some of the rounds of key lock, and it'll also cache them, because if you need to repeat the same calculation repeatedly, it's easier to just like look them up in an array. There's an option here, use known key. So use known key can specify, you can go, I already know 56 bits of the key, just get me the last 8. So, but if you set the defaults, it'll completely ignore the known key that you put here. So you just enter the known key as one giant integer, put the known key length in, and it will pre-calculate that and then try to attack like the next few bits of the key. So it will generate, so the linkage here is not the Hamming weight, it's the Hamming distance. So which is the difference in the number of ones between two states. There's no hard and fast rule on this. This, like, sometimes the Hamming weight works, sometimes Hamming distance works. It depends on algorithm and specific implementation. So yeah, it effectively brute forces 8 bits of the key, and then tries to determine which one closely matches the actual power consumption. The key that I've programmed into this is like 1122 all the way to 88. So I'll just show you it recovering the first bit now. HCS 301. And again, this data is all available on GitHub, so you're free to tweak the parameters, have a play at your own pace. With this, the attack is successful enough that you don't actually need to specify any points. You can just go give me like what it looks like across the whole thing. Across every single trade, shouldn't be calculating intermediate values. That is weird, but that's okay. And so what it does there, it pre-calculates. It goes if, given the known value of the key, I already know some of the keys, so I'm just going to pre-calculate that and cache them. So when I'm guessing all the key bits that I'm going to attack, I can just calculate the final few bits of the key. I might just fix that now. Forgive me, I should prepare demos better than this. I didn't save the edit. Good. Oops. Okay, so all that's going to do is I'm just going to attack the first 8 bits of the key. It should come back as 0x11. It's a little bit slow. I can just show you some of the results. So what will happen is that you'll see a graph like this, where you'll notice a significant correlation peak for the correct key and the correct key only. And then you can feed that key back in. I don't know why it's so slow today. Anyway, as you calculate bits of the key, there we go. So you can see that it's correctly recovered the first bytes of the key, 0x11. Here. We can feed that back in to recover the next byte of the key. So as you can see, I already did this a bit, but what you do is go that. You go, I only know 8 bits of the key, and then you set the use known key to true. You perform the attack again. This time it will correctly calculate the intermediate values, given the first byte of the key is 0x11, so it'll calculate the last 8 rounds of keylock. So in this case, and I think we touched on it earlier, because we only know the ciphertext output of keylock, we actually need to go backwards. But that's okay, because we know the ciphertext, we can still infer information about the intermediate state based on a key guess. So it's enough information to begin this type of correlation attack. This is also applicable to other algorithms such as AES. I don't have the code in this repo, but it's absolutely possible to do. So here you can see that it's now selected 0x22 as the second key byte. Doesn't like Control-C, that's all right. You can keep going until you've recovered the entire key. The data's there, you can reproduce the experiment. And what you'll notice, for round 3, it'll suddenly become 0x77. Please do not be concerned, that's just the keylock key getting shifted. The rest of the key bytes will come out in order. Okay, so that's it. I mean, with that information, you've recovered the secret key to a keylock remote, and you can just program your own keylock remote without needing Roldan. You can permanently clone them and distribute them around. There's a lot of further work, so like this isn't all I've got. There's a whole lot of targets that you can apply this to, and I think a lot of interesting ones. So I'm looking at things like early boot of microcontrollers, so like secure bootloaders, encrypted memory smart cards, I think is a really interesting one. And there was a bit of work done recently about like ways to extract this information from NFC cards. So even though you can't measure the power directly, you can process the energy that it's consuming from the NFC reader in order to get a side channel, like enough information to perform side channel out. So I'm quite interested in that. Yeah, and I am keen to collaborate if people are interested. And that's all. Thank you everyone for listening to me rant for like an hour and a half. Are there any questions?
Thank you, Norm. That was pretty much lots of content for 6 p.m. I should say. Are you still there? Yeah. I hope I didn't lose you. Oh yeah, there are a few questions. Maybe I can start with some of the questions posted here, and I guess you addressed some of those, but let me just read it out for you. In one of the examples that you were talking about, okay, here is the start of the AES operation. So the question is, how does one go about capturing the moment that the AES operation is happening? Okay, fantastic question. In the examples that I've shown today, I've done it because I control the target firmware. I just go, hey, I'll set like one of the pins of the target high, and it'll go, okay, I'm starting AES now, and I can start capturing from there. For a real target, there's two broad ways to do it. Firstly is if you're feeding input into AES, or like if you can press a button and start AES, you can trigger off that. You can trigger off the input. A second way to do it is you can perform a low pass filter over the entirety of the power trace, and then as long as you trigger before the operation, as long as you capture like the beginning of the operation that you're interested in, you can kind of just because AES has a distinct round structure. So you apply a filter, you apply a low pass frequency filter, you go, oh, hey, there's the 10 rounds of AES, and then you just line them up, and then you kind of don't need a trigger. That introduces error though, because the alignment process is not absolutely perfect. Sometimes it will have like false alignments. In those cases, it can, like, an easy way to fix it is just to take more traces. So the ones that are incorrectly aligned don't contribute as much to the correlation score. Right. Cool. The other questions, some people that posted both on IRC and YouTube was, can they get the, again, link to that GitHub repo that you mentioned at the beginning of the talk? So maybe that's something we can post it.
Okay, sure. Yep.
I'm just double checking if I'm missing any other questions. But guys, if you have any questions, please post it now. But I do have a couple more. One thing about the key lock. Did you mention like what is the typical length for the key?
The typical length for key lock, or well, the only length for the key, as far as I'm aware, is 64 bits.
And when you were doing the group analysis, and you kind of the moment that you mentioned that, you know that this is like a cold start, like the time that there's a waiting time, and then you move to, okay, this next block is related to the EEPROM.
Yep.
Was it you reading the spec and finding that out, or was there any other hint or some differential notices that you actually know, okay, this is the start of the crypto part?
Okay. So I'm going to just go back to the slides again, and this might make it a bit easier to talk about. Okay, so there's an overview of the trace, or there's an overview of the trace. There's only a few things that I'm really interested in here. So the first part, underlined by red, and the part here is not relevant. And I know that from the spec. I know that from the datasheet, which says there's a fixed amount of delay time, which corresponds to that section. So I ignored that straight off the bat. This next, the big change in power consumption was identified by the guys in 2008, I think. And the way that they did it was by, what they do is that they'd run this a couple of times and then reduce the power available to the chip or like stop it entirely when it was doing this operation. What they noticed was by like causing this operation to fail, that the rolling key would not move forward. So they figured out that this was an EEPROM operation. The remainder of that, there's only really two other possibilities of interest, which is this block here and this final block here. Like there's only two possibilities. So like you can just brute force. You know that when you get to this point with the big spikes, so that's when the RF transmission happens. You know that that's too far, because by that time that happens, like the chip already has worked out the key lock output.
All right, thanks. And one, perhaps the last thing is specifically for people, you know, wanna start this power consumption type side channel. And I guess a lot of concepts and things you spoke about may not be necessarily an area that a person with a computer science type background will know. Do you have any recommendation, like where they can start, things that in particular you think is important for them, specifically on a fundamental type knowledge that they have to know? You also touched on a number of statistical type algorithm. Like what are those things that you think someone has to know before they want to explore this area a bit more? And I know you had quite a really limited time for you to explain everything, just so they can take away.
So good question. So like I come from like a traditional computer science background. The way that I did it was I went and had a look at how. So I got a chip whisperer ages ago. One of these. Ignore the extra bits. They're not there. It'll look like this. And what it is like it's a pre-built hardware toolkit for doing this kind of attack. And it's got a few optimizations when you control the clock into the target. So it's really good. Like it does like a subset of this attack. And I built my software and built my attacks on the basis of how Chip Whisperer was doing its attacks. So I'd look through its source code, I'd experiment with the Chip Whisperer and go, okay, this is kind of how it works. And there's like, to be honest, there's not that many resources on this. It's a little bit of like an obscure niche topic. The guy who makes Chip Whisperer, so Colin O'Flynn, he's got a couple of things on YouTube. It's worth taking a squeeze at that. Otherwise, it's reading through source code. That's how I did it. I don't think that there's a real like single repository of information. There's some, I think there's some people who've made GitHubs before of like differential attack like resources. So look, like if you look for like a resources for DPA attacks or CPA attacks, you might get some links to have a look at. But yeah, like unfortunately, there's no single easy way to learn it.
So kind of, from my understanding, effectively you picked up the Chip Whisperer to look at the source code. Was there any particular target you had initially when you were investigating this area? No. Like it just seemed interesting. And it seemed like a really powerful attack technique that I could apply to lots and lots of different things. I started off by just looking at an 8-bit AES implementation. The reason why that's good is because the SBox operation that we talked about earlier, where it XORs your plaintext with a key and then use that as a key to a lookup table, the Hamming weight of that is disconnected from the Hamming weight of the key. So what you get is like a very strong and very consistent leakage out of the output of that. And it has, in my experience, fewer false positives than if you attack, I don't know, like Keylock or another target. So I just looked at AES. I started with that and I built, where is it? So, hey, here it is. Okay. I built this, and like you can just program your own like crypto algorithms on that and test at your own pace.
And the chip whisperer guys also sell pre-made target boards with a variety of algorithms on it. And you can go online and just like download, triple DES for AVR. So there's like, I started on AES, but feel free to start anywhere.
Great. And perhaps the last one will be mainly around the traces that you have captured and the key lock example. How long were them and how many of those were there?
Okay. The traces I captured for keylock, so I can't remember off the top of my head all of them. For keylock, I did I think 100,000 point. We can test. I'll just quickly test now. Let me have a look. Okay, so I captured 80,000 traces at 80,000 points at 125 megasamples a second. So that I think it works out to like 2 milliseconds or something like that. And I captured 200 traces from memory.
That's quite a lot. Cool. Thanks again, Norm. If I'm right, we don't have any other questions, but as Norm mentioned, please do reach out to him. You can find him on a Slack. This is his handle. And I think also I need to revisit this talk again to digest lots of things that you talked about, but I can imagine there's lots of things you need to cover just to start explaining about how the attack can work. But again, thanks again, and thanks everyone who joined us tonight. And please do tune in for our upcoming talk in July. It will be on our usual second Tuesday of the night, 14 July. And it is an exciting talk. It will be around Docker or container security from a person who himself is a bigger contributor to the whole how to make run C and things like that more secure. And with that, thanks again and see you next time.
Cool. Thanks. See ya.